All right, back at this. So for Mau's theorem, we said that if f has local extrema, then they occur at locations local extrema, they occur where f prime of x, the derivative, is equal to 0, or where f prime of x does not exist. So you said that. Those are local extrema. Global extrema can occur at local extrema. There's one other location where they can occur. Global extrema, this is not a part of Fermat's theorem, but we can use Fermat's theorem to state it. Global extrema occur where there's 3 locations where the local extrema occur. F prime of x is equal to 0, or where f prime of x does not exist, or last part, at the endpoints of the closed interval on which the function is defined. Interval. Okay. Let's see. These places here where the derivative is equal to 0 or the derivative does not exist are kind of special points. We said that the mins and the maxes can occur here. We actually give them a particular name. These are called critical numbers, or critical points if you prefer. Well, I take that back. They're not quite the same, but they're close. They're related. So critical numbers are in fact those numbers where the derivative f prime is equal to 0 or the derivative does not exist. If I want to find the point at which this happens, so this is the xy pair, this is called the critical point, for which that x value c is the critical number. So another way that we could say find global extrema is by doing the following. We call this the closed interval method for finding absolute extrema or global extrema. So we have the criteria of the extreme value theorem. We have a continuous function, so a closed interval. We start by finding those critical points. Find where the derivative is equal to 0. Find where the derivative doesn't exist. Second, I'm going to list the endpoints. These are all x values, particular x values that I'm finding. X values. And again, these are x values. That should be given to you in the context of the problem. These ones. After that, I want to find the related y values. Find the function values at those critical points and endpoints. I'm looking for maxima and minima. Therefore, I'm looking for where is the largest value, largest y value, and where is the smallest y value. Those are the absolute maximum and minimum, respectively. So let's do a problem, or 2, or 3. I'm going to clear this. There we go. Okay. So if I'm given the function f of x is equal to x squared minus x, and it's defined on the interval from 0 to 2, let's find the value and location of all global extrema. Find the value and location of all global extrema. Global extrema. Okay, here we go. First, I need to find the critical points, which means I need the derivative. I'll go ahead and note that. Find the critical points. I need f prime of x. I have a function f above. I can take the derivative of it. Derivative of x squared is 2x minus the derivative of x, which is 1. Okay. Critical points occur where f prime of x is equal to 0 or where f prime of x does not exist. Now look at those locations. Where f prime of x is equal to 0, well, I'm going to take that derivative, 2x minus 1, and set that equal to 0 and solve. So this becomes 2x is equal to 1, which means x is equal to 1/2. That is one critical point, which I will denote as CP. So this is one possible location for an absolute maximum or minimum. Similarly, where f prime of x does not exist, well, this function here, that's a polynomial. It's defined for all real numbers. So there are no locations where this derivative does not exist. So I might say no such x values. Or you could just put NA for not applicable if you prefer. So I have one critical point. So I have critical point x is equal to 1/2. End points are the two other x values that I'm looking for. X is equal to 0 and x is equal to 2. I have 3 locations I need to check for absolute max or min. I'm going to put all 3 of those into the original function. I'm going to put all of these into the function f of x is equal to x squared minus x. The function, not the derivative. I'm looking for y values here. So f of 1/2 is equal to 1/2 squared minus 1/2, which is equal to negative 1/4. F of 0 is equal to 0 squared minus 0, which is 0. And then f of 2 is equal to 2 squared minus 2, which is equal to 2. So there's my list of possibilities. This is the largest y value. This is the smallest. So that means that f of 1/2, which is negative 1/4, is the global, and f of 2, which is the largest y value, is the global maximum. So that means the point 1/2, -1/4 is the highest, lowest, excuse me, lowest, and the 0.22 is the highest point. So the location of the global minimum is 1/2. The value is -1/4. The location of the global max is 2, and the value is also 2. So that is how we would use the extreme value theorem to find global max and global min. Excuse me. Let's do another example. Let's clear this and go to the next page. Okay. Let's see here. What if we're given the function f of x is equal to e to the x plus e to the negative x divided by 2. And I'm going to define this on the interval from -1 to 2. And now I want to find global extrema. Find the value and locations, values and locations of global extrema. Okay, so I'm going to rewrite this just to make it easier on myself. This is 1/2 e to the x plus e to the negative x. It's a little bit easier to read. And I'm going to start by finding critical points. Critical points. I need the derivative to find critical points. So f prime of x is equal to that constant 1/2 times the derivative of e to the x plus e to the negative x. Derivative of e to the x is e to the x plus, well, the derivative of e to the negative x is e to the negative x times the derivative of negative x, which is -1, which I could simplify as 1/2 times e to the x minus e to the negative x. So there's my derivative. Now, I want to use it to find critical points. So places where f prime of x is equal to 0. That's one location. So I'm going to find where 1/2 times e to the x minus e to the negative x is equal to 0. I want to solve that. Divide both sides by 1/2. That gets rid of the 1/2. E to the x minus e to the negative x is equal to 0. Let's see, how could I do this? I'll add e to the negative x to both sides. E to the x is equal to e to the negative x. Okay. I'm going to clear this pane. So I have e to the x is equal to e to the negative x. So I'm going to rewrite e to the negative x as 1 over e to the x, because that makes it a little easier to deal with. Multiply both sides by e to the x. So I have e to the x times e to the x, which is e to the 2x, is equal to 1. That I could think of in one of two ways. I could rewrite it as a logarithm, which is probably the easiest way. Natural log of 1 is equal to 2x. Natural log of 1 is 0. It's equal to 2x, which means x is equal to 0. So one location where the derivative is equal to 0.
second place that critical points can occur is a place where the derivative does not exist. Let's see, where could it not exist? Note that 1/2 e to the x and e to the negative x are defined and continuous for all values of x. All values of x. And I had a theorem in the first chapter that said the combination of continuous functions is also continuous. So 1/2 times e to the x plus e to the negative x, which is, minus e to the negative x, which is a combination of those functions, is also defined and continuous. Defined and continuous. Continuous for all values of x. All values of x. This is the derivative. This is f prime. So again, there are no x values that make the derivative not exist. I would say NA for this one. And again, my video is pushing 15 minutes, so I think we're going to stop it and start another video.